Hello students, in the previous module on complex numbers and analysis, we discussed the Cauchy's integral theorem. In this module, I am going to discuss another very important result. This is called the Cauchy's residue theorem, or simply the residue theorem. Okay. So before I do that, let me first tell you that suppose I were to give you a function z to the power n, where n is an integer. What is this? Okay, where n is 0, 1, 2, 3, and so on. And let me say that I am giving you a contour. Okay, that indeed encircles the origin. Okay, this is the origin. Okay. Okay. So now, in the last module, we saw that integral dz over z, okay, over this contour C was 2 pi I. What about this when n is positive, a positive integer including 0? Now, with the help of Cauchy's integral theorem, what does Cauchy's integral theorem say? Integral f of z dz is 0 if f of z is analytic inside C. Right? So z to the power n for n positive is certainly analytic inside C. You can ensure that it satisfies the Cauchy Riemann condition, as well as it is not singular at the origin. So without actually doing any work, you can immediately say that the answer to this question is 0. Okay. Of course, this is over the same contour that I have, some arbitrary contour that I have drawn here. Now, how do I, well, if you say that, well, you want to verify this explicitly, right, we can do this as well, right? So you can say that I'm going to take. Now, you also know that with the help of residue theorem, and you can bend the contours as long as you do not cross any singularity. So let's say we'll take a circle about the origin, okay, as our contours, some circle of radius r. Okay. Okay, let me try to draw it using the. Okay, so if we do this, then so let's say this is our contour C, z is r e to the I theta, right? And let's say r is 1, it's a unit circle, right? Radius is 1 for simplicity, right? So z is simply e to the I theta, dz is e to the I theta, I d theta, right? So integral dz z to the power n is I 0 to 2 pi e to the n plus 1 I theta d theta. That is always 0. You can verify it for n greater than 0. Okay, this is easily verifiable. Suppose I ask a slightly different question. Take the same contour. This is of course real and imaginary, even if I don't mention this, right? Suppose I say that I'm interested in calculating dz by z to the power n plus 1. Note that we have already shown that integral over dz by z, okay, over any contour that encloses origin, including a circle of unit radius, is 2 pi I. What about this? Okay. Now again we have to do the so the pole is of nth order at the origin. The pole is of n plus 1th order. It's 1 over z to the power n plus 1, right? And C is a unit circle, right? So z is e to the I theta, dz is I e to the I theta d theta, and therefore the integral becomes theta is 0 to 2 pi I e to the I theta by e to the I n plus 1 theta d theta, that is I 0 to 2 pi e to the minus 2 n I theta d theta. Okay, and remember that n goes from 0, 1, 2, 3 and so on. Okay, when n is 0, this is 2 pi I because the integrand is just 1. So integral 0 to, so let's write this explicitly. If n is 0, the integral is simply I times 0 to 2 pi d theta, that is simply 2 pi I. If n is not 0, it's greater than 0, okay, then you can verify that this is actually 0. If I say n is 1, it's e to the minus 2i theta, right? Then you will find that it is actually 0, right? So we can therefore say that integral over dz by z to the n plus 1 is 0 except for n equal to 0. Okay, so we can further say that 1 over 2 pi I integral over the origin, where the contour is about the origin, dz by z to the n plus 1 is, you can write this result as in terms of a symbol called the Kronecker delta, which means this symbol means that if n is equal to 0, then the value, if these two things are the same, that is n is equal to 0, the value of this symbol is Kronecker delta is 1. If n is not 0, if these two things are different, then it becomes 0. Okay, now so this is a very, very important result again. Now if I were to say that the contour is not about the origin, right, I have the complex plane, it's an arbitrary contour about some other point A, okay, then you can generalize this result to say that dz by z minus a to the power n plus 1 is delta n0. Okay, this is a very, very important result. Okay, now let's discuss what is called a very famously called the residue theorem. It's a very, very important result. Sorry. So let's discuss the Cauchy residue theorem, simply called the residue theorem sometimes. Suppose I say that you have a function, you have a contour first, a closed contour. Remember that all these theorems are for closed contours. So we'll come to the importance of closed contours when we want to evaluate some integrals. Let's say that you have a function f of z which is defined about a closed contour, and there are some finite number of poles as singularities. Okay, so let's just write this explicitly. F of z has finite number of poles as singularities. Okay, now right, so then I am interested in again calculating integral over this contour of f of z dz, where f of z is not analytic but it has a finite number of poles. Okay, now the residue theorem says that this is nothing but 2 pi I times sum over all the poles and residue of the function at all these poles. Okay, this is the residue theorem. I'll of course justify why this makes sense in a minute. Let's just say that this is the residue theorem. Okay, now how do we justify this? Okay, let's imagine that, okay, let's first put the poles. There are, let's say, 4 poles just for the sake of argument. Now because I know that I can bend this contour as per my will, as long as I do not cross any of the singularities, I am going to now bend this contour in this fashion. I am going to say that let me draw a line. Okay, and then another line very close. I'll explain what I mean by this, and then from here I'll draw another line and then another line. Okay, all I'm doing is I'm trying to redraw this contour. Excuse me. I'm just let me move this pole inside. Okay. Oops. Let me draw the pole after I draw the contour, because okay, let's say the pole is here. I'm drawing a tiny circle about that pole, right? And in a counterclockwise sense, and I come here all the way, and then I go here, and then here I draw another tiny circle. Okay, again in a counterclockwise sense, and then go like this, and then let me erase the pole, then draw the pole after I draw the circle, right? Okay, now I again go back. Let me okay, let's say we have only 3 poles. Okay, just for the sake of argument, it doesn't matter, you can generalize it to any number of poles, right? So I have deformed the original contour which was shown here, so let's assume that there are only 3 poles, such that I'm enclosing only these 3 poles, and when I go from one pole to another, I go in a straight line, and then I come back very very closely to the previous line in the opposite direction. So you know by now that these things are going to cancel out. These two contours are going to cancel out. Same in the similar manner, these two contours also are going to cancel out. That means that integral f of z dz over a given contour is nothing but, now all that matters is only you have 3 circles. Okay, you have one circle in a counterclockwise sense, another circle, and then third circle. So we know how to do these things, because you have only first order poles. These are of the form dz by z minus a integral over that particular pole. This is just nothing but 2 pi I. Each of these circles will give you a 2 pi I. Okay, and here of course we don't just have dz by z minus a. You have a function. Okay, so what one imagines is one expands the function about each of these points in a Lorentz series, and what you will pick up is just the derivative of that, the residue of that function, which is the coefficient of 1 over z minus a or z minus b or something like that. So all that will happen is this will give you 2 pi I from each of these poles times sum of the residue of the function at each of these poles. I is equal to 1 to n or whatever is the number of poles. Okay, this is basically called the Cauchy's residue theorem, or simply the residue theorem. Okay, the residue theorem is very very powerful because it will help us in calculating several integrals, as we will see shortly. I'll give you a couple of examples. I'll give you many examples as we go along. So let's take one of the simplest example. I have a complex plane. Okay, and of course, as usual, real and imaginary. Now let's say my function is 1 over z squared plus 1. I can write this as 1 over z plus I times z minus I, right? So there are 2 poles, one at I and one at minus I. Okay, now if I were to take a contour right about the top pole, okay, now what is the value of the contour integral of this function? So what is integral? Let's call this C1 about the top pole at z is equal to I. What is integral f of z dz? That is nothing but from the residue theorem, it's 2 pi I times sum of residues of the function at all the poles, but here we are encircling only one pole at z is equal to I. So 2 pi I times residue of the function at z is equal to I. So how do I find the residue of this function at z is equal to I? What I do is I say that it's 2 pi I times, right, z minus I times the value of the function 1 over z plus I. Okay, let me back up a little bit. Is equal to limit z tends to I 2 pi I times, right, this is the formula for residue, times z minus I. So these two terms will cancel, so you will get, if I take the limit as z goes to I, this will give me a 2I. So the answer will simply be pi. So integral over dz by 1 plus z squared over this contour, okay, that's very, very important, is simply pi. Now you may say that you don't want that contour, you will have some other contour, C2 over the lower pole at z is equal to minus I. Then you can verify that integral over dz by 1 plus z squared is, now it is 2 pi I times the residue at z is equal to minus I. Again, it's the same function, so the residue can be calculated as z is equal to minus I 2 pi I times z minus minus I, which is z plus I, times 1 over z plus I z minus I. These two things will cancel. Now as z goes to minus I, I'll pick up a value of minus 2i. That minus 2i will cancel with plus 2i to give you a value of minus pi. Okay. Now you may say that well, why just pick these two contours? Let's pick some other contour. Okay. Let's say, let me first remove these older contours. Let's say we'll take a new contour that encircles both these poles. Okay, now let's erase all this. Let's call this C3. The new contour is C3. Now integral of the same integrand 1 plus z squared over C3. Now you have two poles and you have to sum over the residue of both these poles, but the residues are just plus pi and minus pi. The answer is 0. So depending on the contour that you take and the nature of the singularities, how many are there, the value of the integrand will change quite distinctly. Now I'll just do one more topic and then end this module. This is a very, very useful formula which is a corollary of the the residue theorem. It's called the Cauchy's integral formula. Okay, what does this say? Suppose, let's say I have a function f of z. Let me write it like this. I have a function f of capital F of z, which is written as f of z by z minus a, and let's say I take I'm sorry about this. In the complex plane, I take some contour, and this is z is equal to a. Let's say this is the counterclockwise contour we are taking. Now, therefore, f of z, capital F of z has only one pole, and let's assume that this is analytic. Let's call this contour C within C. Okay, so if you apply residue theorem and ask the question what is integral f of z dz over this contour, right, you will find that it is nothing but there is only one pole at z is equal to a. So the residue is simply 2 pi, I mean the integral is simply 2 pi I times the residue at z is equal to a, which is simply f of a. Or in other words, instead of capital F of z, if I write it as f of z by z minus a, and I pull down this 1 over 2 pi I here, is simply f of a. So this is a very neat result. I'll point out why it is a very interesting result in a minute. Okay, this is called the Cauchy's integral formula. Oops, I'm sorry. This is the Cauchy's integral formula. Now, why is it so neat? Note that, let's understand this in a minute in a little bit detail, right? Note that this, let's say this is the complex plane and this some contour in counterclockwise direction C, and this is the point z is equal to a, right? Z is equal to a. What is the integral theorem saying? Integral f of z by z minus a is f of a. Note that this is the integral over this contour. So the value of the function and value of the denominator, everything lies in this contour only, right? Because it's the integral over this contour. But you are able to get an information about the value of the function within the contour just based on the values of the function on the contour. So this is a very, very powerful result, right? Suppose I say that you know all the values of the function over a boundary, and then based on that you are immediately able to say what is the value of the function inside, right? So that is a very, very powerful result. Okay, so there's one last point about residue theorem. Suppose I say integral e to the 1 over z dz over over the origin. Note that this is an essential singularity. But if you have a Lorentz series, it will still have a term of the type 1 over z with coefficient 1. So the residue of this function of the essential singularity at the origin is 1, right? So this also is simply 2 pi I times 1, which is simply 2 pi I. So you can do integrals rather quite powerfully, just by doing, you don't have to do anything. Suppose you say that you have a contour that encloses the origin, then you can immediately find out what the integral is. Suppose I say same contour about the origin, but e to the 1 over z squared. But e to the 1 over z squared does not have a term of the type 1 over z. So the residue is 0. So this integral is 0 because there is no term, if I expand e to the 1 over z, that is of the type 1 over z. So that means that there is no coefficient of 1 over z, therefore the residue is 0. So this is again a very, very powerful result. So what I will do is I will stop this module here, but in the next module on complex integrals, I will try and tell you and explain you by with the help of many examples how this residue theorem can be used to evaluate various integrals, both real and complex. Okay, I'll stop here and we will again continue in the next module. Okay,